It works? Yeah, okay, thanks. Okay, so I'm Samir, and I will be just briefly overviewing the For You projects that aims at formally verifying YUL level static analysis and optimization with the Proof Assistant ROC. Okay, so the context of this work is formal guarantees for compiler correctness. Since compilers rely heavily on static analysis and optimizations, and these implementations, the implementations of these tools can have implementation bugs. Even if the underlying theory is correct, the correctness of the entire compilation process depends on these components being correct. So our goal is to provide formal mathematical guarantees that these tools are correct. And we want to do it with formal verification. So formal verification of programs, of correctness of programs can be done in several ways. One popular way is to use a proof assistant. So in this context, you have a language that is usually a functional language with algebraic data types. And you can write programs and then write statements about these programs. The statements are written in some logic that is supported by the proof assistant, and then the proof assistant will help you to prove the correctness of these theorems, step by step, where every step is verified to be correct. So if you want to use this approach to verify a static analysis tool, the tool must be written in this language of the proof assistant, which is not realistic because these tools are not usually written in some other languages. So what we can do, we can build a model that represents the static analyzer. We can build it in the language of the proof assistant, and then write proofs and statements about the correctness of this model. The challenges here is that first we have to trust that the model really represents the behavior of the static analyzer. So this is something that we have to accept. Also, static analysis tools typically use external tools as SMT solvers. So either you model them or you have to trust that they are correct. And also writing proofs at this scale is very complex because the tools are very large. So an alternative approach that instead of verifying the analyzer itself, we can verify the results that it generates. So in this approach, we have a program, we run the tool that is the static analyzer, and then we get a result. And when we pass the program and the result to a checker that we write, and the checker tells me if the results are correct or not. So the idea is that this checker is much simpler than the tool itself, and we can write it directly in the language of the proof assistant, and then we can write formal statements about the correctness of the checker, which means if the checker tells me that the results are correct, then they are really correct, okay? And we develop the proof for these statements in the proof assistant. So this approach is a bit more realistic than the other one. Okay, so it doesn't matter which approach you take, verifying the tool or verifying the results. In order to write formal statements about programs or about the properties of programs, we need to model the behavior of programs mathematically, and here comes the role of semantics. So we have to develop a semantics in the proof assistant that represents the semantics of the programming language that we are dealing with. And we have part of the semantics also we have to represent data types and the states, and everything has to be defined in the proof assistant. Okay? The semantics that we usually use is operational semantics, which describe discrete execution steps, how from one state we can move to the next state. And these operational semantics can be defined either as an executable function, so you can execute the semantics like writing an interpreter, or it can be defined as a relation. Simply, you define a logical relation that defines relation between a state and the next state. And in this case, the transitive closure of the relation represents the executions. Okay? So apart from operational semantics, we can also define other kind of semantics. This depends on the property that we are interested in verifying. So the For You project is exactly about this. It's about developing semantics for the YUL intermediate language in order to use it with a long goal term is to use it to verify static analysis results in the Solidity compiler. So we have developed these formal semantics for YUL and the proof assistant cog. The semantic is parametric in the dialect, and we have the AVM dialect implemented, almost executable when possible. The current semantics works at the level of the controller flow graphs, not at the level of the SST. And for a future work, we plan to also develop similar semantics for the AST. As a proof of concept, we have verified the results of the liveness analysis in the Solidity compiler. Like we have developed a checker to check that the results of the liveness analysis that has been presented before is correct. Okay, so let me just briefly describe the components of the semantics that we have. So here we have the interface for the dialect. So if you want to implement a dialect, you have to provide a type for the basic values, like 256 bits. You have to provide a type for the opcodes that are supported, like add, sub, and so on. And you have to provide a type for the state, which is in the EVM, it would be a combination of memory and the store. And you have to provide a method, function, execute, or define a corresponding relation, which says how you execute opcodes in this dialect. Okay, so this function receives a state, opcode, a list of input values, and returns output values, a new state, and the status. The status can be, for example, still running, reverted, an error, and so on. Smart contract, the type for a smart contract is this one. So a smart contract has a name, it has a list of functions, and the name of the main function. The function is represented as a collection of blocks that represent a control flow graphs. So a block includes instruction of this form, assignment, a call to a dialect, or a call to a function. Blocks also have information on their kind, like if they are normal blocks, branching blocks, or return blocks. And also blocks have a support for the fifth function in case you want to represent SSA CFG. Like the CFGs that we have, they do not assume SSA, but you can also represent SSA CFG. So a state at the YUL level is a record of a call stack, like in any other language, where every frame in the stack corresponds to the execution of a function. So it has information on which instruction it's currently executing. It has information about the values of the values of the variables, the current values for the variables, the status of the execution, if it's running, reverted, terminated, and so on. And also a component that represents the state of the dialect, which is managed entirely by the dialect model. Then the semantics scheme is defined as two functions. The first one is a step, which describes how from one state I move to the next state. And eval is just a loop calling steps n times. So those can be defined as an executable functions, or that like what we have them, or they can also be defined as relations. They don't have to be really executable. Okay. So as a proof of concept, we have used these semantics to verify the results of the liveness analysis. So liveness is, we say that a set of variables is live at the beginning of a block if any execution starting from this block is not affected by any variable that is not in that set. Okay. So we have developed a checker for the liveness, which takes a program and liveness information and tell us if the results are correct or not. And so the checker is implemented in the proof assistant ROC, and it is also formally verified. So the statement that we have proved is a statement which basically says if you start from a state ST1 and in execution steps you get into a new state ST1 prime, then if you start from an equivalent state up to the value of a variable that is not live, you will also be able to make an execution step and arrive to a state that is equivalent to the previous one. Okay, so to wrap up is so the success in verifying the liveness information, or in this liveness checker, somehow confirms the feasibility of this approach. We have applied it currently to a small limited of smart contracts just for testing the checker. We will apply it to a broader range of smart contracts. We also plan to extend it to more static analysis that are like concept propagation. But maybe this will be delayed until we define the semantic at the level of the AST, because many of the static analysis are at the level of the AST semantics. And we plan also to improve the usability of the tool by building friendly user interfaces, like to use it from a command line, from a shell, a library, and so on. And of course, to build corresponding semantics at the level of the AST. That's it. Thanks a lot.
Thank you so much, Samir. That was a super insightful talk. We have one question for you. Why rock out of the options?
Because I have more experience in rock.
Pretty straightforward answer. If you folks have any more questions for Samir, yeah.
Great talk, thank you. Can this framework in Rock can be used to formally verify contracts, like to translate them into YUL and prove properties about them?
Sorry, can you repeat again?
So can you use this framework in YUL to prove properties about smart contracts in YUL?
About smart contract, yes. I mean, you can do it also about smart contracts. But then the problem, if you want to verify properties of a specific smart contract, then a better approach is to model your smart contract in Coq and try to prove the property. Like this would not be really appropriate for a single smart contract. It will be appropriate for a tool that receives as input a smart contract, like a static analysis.
Thank you.
Thank you so much. That will be it for you, Samir. Thank you so much for your talk.